pagi Pak Agung.
Ya, selamat pagi Bu Ginting.
kelas dengan antar
Statistics work in very in the development of industry and technology. We established cooperative relations with universities at home and abroad. Companies that have been established and will continue to our needs. The sporting facilities as it has class role. Basketball court, as well as public
Dan di statistika ITS kita juga belajar tentang komputasi. Dan banyak banget hal yang bisa kalian pelajari di statistika di luar dari hitungan. Dan implementasinya di kehidupanku, aku jadi tahu gimana caranya mengolah data yang baik dan benar. Dan ini berguna banget di kehidupan sehari-hari untuk membantu kita mengambil sebuah keputusan.
Di Departemen Statistika, terdapat akademik dan non-akademik. Di akademik sendiri, aku mempelajari tentang pengantar metode statistika, analisis numerik, dan desain eksperimen. Sedangkan non-akademik, aku tergabung dalam staf himpunan statistika dan staf UKM Pramuka.
Kami berkomitmen menjadi lembaga pendidikan dan pengembangan statistika bertaraf internasional yang berkontribusi dalam ilmu pengetahuan dan teknologi, khususnya bidang komputasi dan sains data, ekonomi dan finansial, sosial dan kependudukan, lingkungan dan kesehatan, serta industri dan bisnis.
ITS Statistik Department, which is located in Surabaya. Institut Teknologi 10 November, or known as ITS. It was first established in 1978, which at the time was one of the areas of specialization and the mathematics department of the Faculty of Exact and Natural Sciences. Along with the changing time in 2020, it officially changed to the Department of Statistics, Faculty of Science and Data Analytics.
Departemen Statistika saat ini telah mempunyai 3 program studi. Program studi S1 Statistika, program studi S2 Statistika, dan program studi S3 Ilmu Statistik. Ketiga program studi tersebut semuanya telah terakreditasi A. Sejak tahun 2019, Departemen Statistika telah mempunyai program kelas internasional bagi program studi S1. Kelas ini disebut IUP atau International Undergraduate Program. Pada kelas internasional, mahasiswa akan diberikan keahlian dan pengetahuan statistika di berbagai bidang dalam kelas dengan pengantar bahasa Inggris dan fasilitas yang lengkap.
From year to year, Statistics Department graduates have worked in various fields. In the development of industry and technology, we have established cooperative relationships with the universities at home and abroad, as well as government agencies and private companies that have been established and will continue to be improved. As means of supporting our needs, until now we have 5 laboratories including that Laboratory Computational Statistics and Data Science, Laboratory Business and Industrial Statistics, Laboratory Social Statistics and Population Studies, Laboratory Health and Environmental Statistics, Laboratory Economics and Financial Data Analytics. We have a sporting facilities below. It has classroom, reading room, trial room, toilets, gazebo, Sigma Garden, basketball court, as well as public facilities such as malls and ITS Central Library.
Dan di Statistika ITS kita juga belajar tentang komputasi. Dan banyak banget hal yang bisa kalian pelajari di statistika di luar dari hitungan. Dan implementasinya di kehidupanku, aku jadi tahu gimana caranya mengolah data yang baik dan benar. Dan ini berguna banget di kehidupan sehari-hari untuk membantu kita mengambil sebuah keputusan.
Di Departemen Statistika, terdapat akademik dan non-akademik. Di akademik sendiri, aku mempelajari tentang pengantar metode statistika, analisis numerik, dan desain eksperimen. Sedangkan non-akademik, aku tergabung dalam staf himpunan statistika dan staf UKM Pramuka.
Kami berkomitmen menjadi lembaga pendidikan dan pengembangan statistika bertaraf internasional yang berkontribusi dalam ilmu pengetahuan dan teknologi, khususnya bidang komputasi dan sains data, ekonomi dan finansial, sosial dan kependudukan, lingkungan dan kesehatan, serta industri dan bisnis.
Yes. Okay. Good morning, everyone. Dear all the speakers of this international seminar series, Professor George Mateu, Professor Hamzah Fansuri, Associate Professor Maria Anityasari, Dr. I. Gede Nyoman Mindrajaya, Dr. Yudi Andriana, and Dr. Ahmad Khairuddin. We are very honored to have you here. Good morning to all the academia at Institut Teknologi 10 November at Department of Statistics, especially the head of the department, Dr. Kartika Fitriasari. Also, good morning to all the committees, lecturers, and participants of the seminar. Thank you very much for attending this event. We are welcome you to the seminar series under the World Class Professor Program entitled Modern Spatiotemporal Statistics and its Application by Statistics Department, Institut Teknologi 10 November. First and foremost, I would like to express my gratitude to God. Apart for any circumstance that we are facing today, we are all happy, healthy, and ready to participate this international seminar series entitled Modern Spatiotemporal Statistics and its Application. The seminar is organized by Department of Statistics, Institut Teknologi 10 November, in collaboration with University Jaume I under the program of World Class Professor. This seminar also held as the series of the events leading to the National Statistics Day on September 26th. Also, I would like to introduce myself. My name is Dwi Ari. On behalf of Department of Statistics, I will hold the role as the host and moderator of the webinar today. In this international seminar series, the participants are joining via Zoom and YouTube live sessions, and some of the speakers are joining offline in the venue. And for all the participants joining via Zoom, please mute your microphone to reduce the noise, and please also turn on your camera. Please feel free to use our virtual background that has been sent by the committee. And we want to inform you that the link for the attendance would be shared by the committee through the Zoom or YouTube chat box during the seminar. So please stay tuned to the seminar and kindly wait for the presence link. The rundown of this seminar will be started by the opening, followed by the speech of the invited guests, the rundown of the seminar will be started by the opening, followed by the speech of the invited guests. And the first speech will be delivered by Professor Hamzah Fansuri as a Dean of Faculty of Scientifics, Institut Teknologi 10 November. And the second speech will be delivered by Associate Professor Maria Anitya Sari as a Director of ITS Engagement. And the last speech will be delivered by Dr. Yudi Andriana as the President of Forum Pendidikan Statistika. Afterwards would be the photo session. And the following session would be the main session of the seminar today, which are the talks by a keynote speaker and two speakers of the parallel session. The keynote speech will be delivered by Professor George Mateo from The keynote speech will be delivered by Professor George Mateo from University Jaume I, followed by the discussion session of the event. And then we have the parallel session by Dr. I. Gede Newman Mindrajaya from Pajajaran University, and then followed by the talk by Dr. Ahmad Khairuddin from Institut Teknologi 10 November. And then afterwards, we will have a discussion session of the two talks of the parallel session. And finally, the end session would be the closing of the seminar today. Ladies and gentlemen, without waiting any longer, let's start the sessions of today's seminar by hearing the welcoming speeches from three invited guests. First, because Professor Hamzah Fansuri has not come to the venue yet, then I will ask Associate Professor Maria Anitya Sari as a Director of ITS Engagement to start the speech of the International Seminar Series today. Please, Professor Maria, the time is yours.
Thank you very, very much, Ibu Dwi Ari, for a wonderful opening, and also my regard to all of you in the venue, Hotel Haris, if I'm not mistaken. I believe all of you now ready to learn a lot from our world-class professor that came from far away. Welcome to Professor George Matthew. Thank you so much, Prof, for agreeing to come and collaborate with us, and also our colleague from University of Pajajaran. So today, as the representative of ITS, I'm Maria, the Director of ITS Global Engagement, would like to welcome all of you to this precious and very, very great opportunity under World Class Professor series. This program is facilitated by the Ministry of Higher Education, Research and Technology to enable researchers from Indonesia to meet and collaborate with researchers from overseas to enhance the science and also technology implementation and publication. On behalf of ITS, I would like to mention one thing that that hopefully will give you inspiration for the follow-up of this program. ITS Global Engagement provide world-class professor program that can support the follow-up of this program. So, my respected colleague, Papa Khairuddin, thank you so much for your initiation to this program. And you will be able to invite Professor Matthew for the second round next year or the year after using the platform of world-class professor that provided by ITS. Not only that, Professor Matthew and also all the colleagues, we also have program like Global Learning Program, guest lecture series as well on SDGs that will be able to be used to invite researcher and also lecturer from overseas to come to our campus for 1 week, and every single expenses will be covered by ITS. By saying so, I would like to highlight that ITS committed to support collaboration, to support and enable any networking, research, publication, and also the enhancement of academic quality of academic teaching in our campus. And also, Professor Matthew, I would like to mention that the ambassador of Indonesia in Spain right now, actually the alumni of ITS. And last week, I managed to meet him. We attended an international education seminar in Barcelona, and I made my way to Madrid and met the embassy there. And we would like to increase the collaboration with Spain, especially by inviting your student and also your young researcher and lecturer, as well as non-academic staff to come to our campus. I hope to see you in person next week during our courtesy visit to our rector or the vice rector, and we will be able to discuss the follow-up of this activity. Congratulations to the Department of Statistics, to Ibu Kartika, the head of department. Thank you so much for managing this event very well. And I really hope all the very best, very fruitful discussion and also publication can be produced out of this program. Once again, thank you very much for all parties that committed their time and energy and also ideas to make this event happen. All the best and have a very great day. Thank you.
Thank you, Professor Maria, for your wonderful speech. Next, I would like to invite Dr. Yudi Andriana as the President of Forum Pendidikan Tinggi Statistika, who has sent us a welcoming remark in advance. Please welcome Dr. Yudi Andriana to give the welcoming remark.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. The Honorable the Dean of Faculty of Sciences and Data Analytics, ITS, Professor Hamzah Fansuri, the Director of ITS Global Engagement, Professor Maria Anityasari, the Head of Department of Statistics, Dr. Kartika Fitriasari, and the Head of Study Program of Statistics at Statistics Department ITS, especially also our honorable invited speakers, Professor George Matthew, Dr. Mindra Jaya, and Dr. Ahmad Khairuddin, all lecturers, distinguished guests, and participants. It is, of course, a great pleasure for me to be part of the opening ceremony of the International Seminar Series of World Class Professor Project on topic Modern Spatial Temporal Statistics and its application, which is quite close to our National Statistics Days, which will be held tomorrow on 26th of September. On behalf of the Indonesian Statistical Higher Education Forum, Forstat, we would like to thanks to the organizer of ITS, especially to the awardee of the World Class Professor Project, and everyone who spent their time to manage this international seminar series. One key performance indicators in all universities in Indonesia is the internationalization program, like research, doing research collaboration, and upgrading academic curriculum. Hence, as a statistical associations, Forsat is also supports the internationalization program and all activities to increase the quality of our members in terms of both research and education. Your willingness to share your valuable knowledge will significantly improve the research culture and upgrade the academic atmosphere here. Again, thank you very much for all your support. I'm sure that all participants will get so many nicely important, new, valuable knowledge from the speakers. Thank you very much and enjoy the seminar. Assalamualaikum.
Thank you very much for Dr. Yudi Andriana for the speech. Okay, because Professor Hamzah has not come to the venue yet, I think we can move to the next session. So before the main session, we are going to have a photo session for this international seminar series. For all the participants in Zoom, please turn on your camera and give your best smile for the photo. For the photo session, please feel free to use our virtual background that has been shared via Zoom chat box. To the committee, please take over the session for taking the photo. Okay, slide 1. Slide 2. Slide 3. Slide 4. Slide 5. Slide 6. Slide 7. Okay, that's all. Thank you for your patience and your help. For all the participants, we want to remind you that the link for the attendance will be shared by the committee through the Zoom or YouTube chat box during the seminar. So please kindly wait for the presence link. Now, we come to the main session of this seminar. We will have 3 talks by 3 speakers. The first talk would be delivered by our keynote speaker, Professor George Mateu. Firstly, I would like to read his profile. He is affiliated with Department of Mathematics of School of Technology and Experimental Sciences, University Jaume I in Spain. He holds He holds his bachelor's degree in mathematics in 1992, master's degree in mathematics in 1995, and doctoral degree in mathematics in 1998 from University of Valencia in Spain. He has several excellent awards. In 2013, he was awarded as the best associate editor of Journal of Agricultural, Biological, and Environmental Statistics. And the most recent awards in 2022, he was awarded as an editor-in-chief and associate editor of the 12 top journals. Also, in the same year, he was awarded as the top 8 amongst the Spanish researchers in statistics and probability. His age index is 26, and if you want to know more about him, you can check his personal website through the provided link. For today's seminar, his presentation would be about spatio-temporal point process models for the analysis of infectious disease. For all the participants, if you have any questions, please drop your questions in the chat box of Zoom or YouTube. Also, if you want to ask directly to the speakers, you can use the raise hand facility during the discussion session after the presentation. Without further ado, I want to welcome Professor George Mateu for the presentation. So for Professor George Mateu, the time is yours.
So thank you very much. I really appreciate it, and it's an honor for me being here and being, let's say, given this kind of prize. It's my first time here in Indonesia, although I know Ahmed for some time now. But it's really a pleasure being here, and really a pleasure sharing this seminar. Perhaps what's coming next, which I think it's the most important thing. I mean, the idea of the seminar is just to bring an overview of a particular field that probably is not that known, or is only known by some subset of the researchers here. And the idea is to motivate people, young students, to start working in the field, and probably linking our relationship between Spain or my particular university and your university here, linking together ideas, research actions, probably international funds, and all these sort of things. So I'm really happy for your invitation here, and I really would like to motivate all the people here, and all the people not only in person here, but also the hundreds of people I can see that are following this seminar online. So thank you very much to all of you. So let me just now share my screen and the presentation. Yeah, that's fine. So when preparing this presentation, this seminar, I thought, I mean, there are several topics we could be talking here in terms of spatial statistics, but I thought that for the seminar, for opening this session, I think I really would like to focus on something which is kind of the small brother of spatial statistics, which is point process models, right? I mean, I know there are many people working in spatial statistics and probably working on aerial data, lattice data, which is also called like that, lattice data, but also geostatistics. but not that many people working on point processes. So I thought that, okay, that's fine. Let's try to motivate people coming into this field, which is point process, which is, you will see, it's a great field within spatial statistics. And the good thing here is that what I'm talking about today is how we can use point process theory to develop our mathematical models and understand how infectious diseases, and in particular COVID data, we're still in the area of COVID data, but how in general infectious diseases spread along a particular region. And you will see that point process theory can say something there. And this is the idea. I mean, trying to react against these infectious diseases by using some stochastic models coming from the point process theory. So this is the idea of this seminar. So for those of you, those that are attending online, haven't heard or haven't hardly heard about point process theory, just try to get the message, try to get the idea. I mean, not going deeper into the mathematical details, but just the idea of how we can use these stochastic models for solving particular problems. So I've prepared something that I've been working with in the last, since pandemic started, so in the last 2.5 years. And basically, you will see here in the overview of the contents that sections 2, 3, and 4 are based on particular papers, very much focused on solving the spread in space and time of COVID data. I'm sure that, after these 2.5 years talking about COVID data and COVID-associated problems, I'm sure that you know everything about COVID data, right? About how the spread of the disease, how this is contagious, how the movement of people affects these sort of things. And probably you've read lots, I should say hundreds or dozens of papers associated to this thing. You will see that most of the papers, they have some common link. And the common link is that or they use mathematical modeling strategies, or they use some statistical modeling strategies. In particular, in terms of mathematical and statistical modeling strategies, they are very, very much focused on what is called deterministic SIR or SEIR models. I'm sure that you've heard about that, but I'm not going and entering into this particular thing because this is very well known and very well used in the statistical practice. I'm going through some different idea, which is trying to detect and trying to mimic what is called the spatio-temporal dynamics in a context where uncertainty is clearly present. And this is essential. Deterministic models are not that useful here because there are a lot of stochasticity. There are lots of something happening and that we cannot really control for many reasons. One possibility is that COVID data is not, let's say it's a data with lots of noise. Maybe it's unsampled. Maybe it's because of whatever reasons we don't have access to the full type of data, or for many reasons we have lots of uncertainty associated with our data. So deterministic models, whether they are mathematical or statistical, they're not that good here. So we are entering a different world, which is the stochasticity and uncertainty controlled by this kind of stochastic models. And one of the good things with point patterns, with this kind of stochasticity, we have what we have in front of us in terms of the data. The data is noisy data, but our models can really go deeper into the structure in the space and time of that data, rather than just developing deterministic models to analyze what we see. And this is very important. We see something which is a noisy version of reality, and we are going deeper into reality rather than on the data we have. For example, this is one particular case. And I don't know if you are used to see this sort of COVID data. What we have here is a classical point pattern case of COVID data. And we will be analyzing this sort of data later on. Here we have locations X, Y, and T's, so geographical locations and temporal location or temporal instant of a particular event, which means a particular individual that has been tested positive or has been gone through the disease. right? So what we have is access to the location of the people that are being infected by COVID. A particular region, in this particular case, is a city in Colombia, which it's called Cali. So this is extraordinary. I mean, this sort of data, I know it's difficult to find because of many reasons. In Europe, for example, it's really difficult to find this sort of data, but we've been kind of lucky to have this thing so that we can use our kind of statistical tools for this. This is an example of 4 different temporal instances of the same thing. I mean, at the beginning of the pandemic, you see that there are very scarce number of points just scattered in the region. Then as time progresses, then, for example, I mean, we started in March, then the second one on the left is May with much more data coming into the region. And then, of course, the data increases and increases when time progresses. So we see this evolution of the data. Clearly, I mean, we have an infectious disease. Something is happening today, and we have infectious all over the region, and the infectious, what it translates is into more and more data as time goes by. This is another type of data, and I'm not talking about this, but just for you to be clear. I mean, I'm sure that you've seen lots of maps like this one. And this is kind of aerial data, so lattice data. What we have is a particular region. Here, there are 2 regions in Spain where the regions are divided into small subregions. And you just count how many events you have in each subregion, for example, per day. So we have, let's say, an aggregated number of data, which is counting random variable per day, which is our time unit, and through a number of days. But again, this is not point parent data. This is lattice data. We are aggregating data into subregions. So this is another way of looking at the same problem. Essentially, when you look at aggregated data, in a sense, you're losing information because you are not going deeper into where something is happening, but just you are counting and aggregating data in some region. So in that case, you are losing some sort of information, right? So this is just for you to say that we are not entering this type of problem, and we differentiate our approach to what we would be doing in case of having this data. Now, this is just for you who want, after the seminar, to go want to go deeper into the details of what I'm telling here. Here you have some references, as you can see in the years. All our references from 2021, 2022. This is the reflect of what we've been doing in these last 2.5 years of COVID data. So clearly, this is kind of very recent research work. So let's start with the first approach. And you can see that there will be a common link here, which is the word space-time, spatio-temporal modeling. So our data behaves in a particular way that has an spread in space, but also has an evolution in time. So we need spatio-temporal tools to work with the data. And in this particular section 2, I will be talking of something which is called a mechanistic approach. And you will see right now why the word mechanistic. What type of data we have here? What we have here is, I think, this is much better in terms of a graphical output. What we have here is a particular area within Valencia city, there in Spain. So what we have here is a region which is divided into 4 districts and 111 census tracts. So what you have here is, on the left-hand side, the building locations in the area. So these black dots here on the left-hand side are just locations of buildings. And on the right-hand side, what we have is the 111 census tracts where the area is divided into. The total number of population living here is around 6,000 buildings in the area. This number, right? And this is the type of data we are analyzing. We are analyzing here, which is sorry. Yeah. So what we can see here is our evolution of the infection, right? So we start from left to right in April, then we go to August, and finally we go to November, right, of 2020. So that was the very first year of COVID, and you see again how the number of points evolve in space and they evolve in time with an increasing number of points in time. So these are our locations of COVID data in our particular area of the city. Well, the very first thing we can do here is some, let's say, just playing with data, what I call kind of a first description of the data. And when we say description of the data, we have to see if our data can be treated as spatio-temporal point pattern or something in space with replications in time. And you see there are two big differences in this type of data. It's not the same thing. I mean, spatio-temporal point pattern means something that is evolving in space and time with interaction in space and time. What is happening in the region in one particular month is very different than what is happening in the same region in another different temporal instant, in a different month, right? And if we had something like replications in time of some spatial data, that would mean that we would have something in space with independent measures in time. And that means something very different. So this relative risk measure tries to see, just as a graphical output, that we have this kind of spatio-temporal interaction. You see, just by looking at the slide, that the colors are changing in space and changing in time. And that's an indication that we have this space-time interaction. And that's important. That's the very first motivation to come on and working into the spatio-temporal structure of the data. So this is just a description that, yes, that we have to work with space and time. But we have something else. It's not only that we have X, Y, and T coordinates, but we have something which is very important for infectious diseases, which is movement of population. We can control and we have information on how people are moving from one place to the other within the city. And that's essential. That's an essential information when working with COVID or in general with infectious diseases. Because, I mean, we as humans, we are transmitting the disease. And clearly, if we move from here to there, this movement is clearly taking the virus from here to there. And that makes a rise in the cases of infection. So we have this data, and we call mobility data. And you see just at the very final part of the slide, you see a kind of way to calculate probability of movement from one area to the other, from area AA to area AJ, right? From A to J in a particular week W. And it's very simple. I mean, a probability is just how many people are moving from A to J on a particular week divided by how many people lives in the origin area. So we have something between 0 and 1, and this is a kind of approximation to probability of movement from one to the other areas. Right, this is an example of movement data. So you see we have like 7 movement areas. So the city is divided in 7 sub-districts, and people are moving from each one of so pairwise movement from each 2 of the areas, right? For example, you can see here on the top right the evolution of this probability of movement to the first area. So from the rest, from 2 to 7 into 1. So how people are moving from the rest of the areas into the first area in terms of probability, it's what it's represented in this top right graph. And what you can see in the second row is just the corresponding metrics 7 by 7 of movement in the different areas, right? So this is the type of information that we have in terms of movement of humans, which is, you will see, it's essential in controlling the spread of the disease. Fine, but again, we have more data. We are in the area of data, and the more data we have, probably the more perfect information we have in feeding our statistical models. So we have these other 4 types of additional, in this case, socio-demographic data. So we have, as you can see, in the area of the city, we have something like the population age 65 years and over. This is one, let's say, one type of covariate information. But also we have the population with less than 18 years. We have an average household income, so kind of economical information. And in general, we have a population density in the area. You see everything having to do with economy, with how many people are living in my area, which is also important, and also how many old people or young people are in the area, because COVID data was very much related to also to, let's say, to old people being infected and having problems of health, of important problems of health. So again, this is information coming into our model. So let's go a little bit more in detail into the modeling framework. So what we have is a classical point pattern analysis here in space and time. So we have coordinates x represent x and y, so in R2 in the plane, and then we have the t's, which represent the temporal instance. Then we have something which is very important here, which is this lambda that depends on space and time. This is the first order spatio-temporal intensity function. You see the expression here, but this expression is telling us something which is very naive on one sense and important on the other, which is how many events, how many infected people I expect in space and time. And this is very important because this is what we are trying to see and we are trying to model. We are providing a mathematical model for this lambda that will provide information on the expected number of infections around particular areas in space and particular temporal instance in time. But this lambda will be conditioned on the history because that's very important. I mean, in terms of if everything were random, history has nothing to do here, but because this is not random and because there is this kind of infectious, there is a history that provides some, let's say, probability on being infected in the future. So it's important to consider this intensity given condition to the past, condition to the history of the process. And this is called the conditional first order intensity function. And it's called, and now appears the word again, mechanistic. When we say that we are providing a mechanistic model, it's because we are providing a particular mathematical expression for this lambda. And this is all what we are doing here. Providing a mathematical expression for the intensity that we can see right now on the screen. Fine, so let's go into this mathematical detail. Now, our lambda, expression 2 here on the screen. Our lambda, you see now that it's conditioned on the history. This h of t is the history, so the past history up to time t. So you see that there are 3 terms here. So lambda is divided, is split into 3 different terms. 2 terms, mu and lambda, mu sub 0 and lambda sub beta, are what is called deterministic terms. So mu sub 0 depends on t. This is a deterministic function in time. It is called a marginal temporal intensity. So everything depending on time that we can control in terms of periodic information, for example, sinus and cosinus and these things, or whatever type of environmental, atmospheric covariates evolving in time, should come into this mu sub 0. Then we have a second term, lambda sub beta, which depends on x, depends on space only, not on time, but on space. And this is called the marginal spatial intensity function. And again, everything depending on space will come into this lambda. And finally, we have something which is non-deterministic. It's an stochastic term in space and time. This is probably the most difficult part of the model out of the 3 terms in equation 2. But we have to go into the 3 just to give an expression for lambda. So let's go in detail into them. So what happens with the first 2 terms? So lambda sub 0. Lambda sub 0 is a function of time, and we go into the most simple thing we can have, which is using what is called a kernel density estimator, which is a non-parametric estimator of the intensity, of the temporal intensity. We assume we have no temporal covariates, So we have no further information in terms of temporal covariates. And the only thing we can do is just providing a kind of a smoothing, which is the kernel density estimator in time. And this is very well known in the literature how to develop this mu sub-zero here, right? A simple estimator. One can say, no, I have something, for example, the temperature, or I could have rain, or I could have humidity, whatever type of, let's say, of functions depending on time. That's perfect. Then you can develop a parametric way of modeling this temporal intensity. But here we go into the most simple case, which is the non-parametric way of doing things. Second term, the marginal spatial intensity. This is given by lambda. So what we assume here is, okay, that's fine, because my region is divided into 111, so 111 census tracts. What I'm doing is I'm counting how many data, how many infected people I have in each one of these particular census tracts. And this is called YI, capital Y. And I say, okay, that's fine because this is counting variable. I assume that I have a negative binomial distribution over there. You could think also of a Poisson distribution, but remember that to be Poisson, there should be no over dispersion. So the mean and the variance should be more or less the same. But we expect over dispersion here. And this is why we do not think of Poissonness, and we think of a negative binomial. That you know that it has like two parameters. The one appears within the brackets after MB. One is Ri, which is like the risk, and the other one is phi that controls this over dispersion. And the good thing here is that we model the logarithm of the risk of Ri by two terms, let's call like that. The first term is given by the covariate information in space. Here we have the density of population. Here we have the number of people, old people living there, young people living there, all these sort of things. So they come into the first part of this logarithm of Ri, which is the risk. But then we have a second part. And again, this is important. If in expression 3, we just remove the very last two terms, U, I, and VI, what we have is a simple regression analysis. It's very simple for our complex data. So one way to reinforce this thing is, okay, that's fine. I have one part, which is a simple regression analysis, but I complete that part with something which is stochastic. And then the U and V terms are random variables. One is called a structured random effect. The other one is called unstructured random effect. Just for you to know, the unstructured random effect is just a Gaussian noise. Something which is, well, I put some noise there because I cannot control the whole thing, and this is given by this unstructured term. And this is V. And the U, the structured term, structure means that there is something I can control, and this something is neighborhood structure. So what is happening in one census tract depends probably on the neighborhood of census tracts. And I can control that. And I do control this by this kind of UI term here. So with this expression in 3, we can have an approximation of lambda, of the intensity in space. With the first expression, we can have an expression for the intensity in time. Yeah, and then we go to the very last term, probably the most complicated one, which is the space-time stochastic term. This rho. What is rho? Rho should be something that provides information on the spread in space and time, something that we cannot see. And this is why I'm saying that this is, on one side, probably the most important term, on the other, the most complicated term, because the data is not telling me how is rho, right? So we need imagination in a sense here, right? So there are lots of, when we need imagination means that we have lots of possibilities. The possibility I'm telling you is one that works here, but of course, to come to the right choice of rho, you need time just to develop the several possibilities here, right? So what we consider here is that rho is the product of another functions which are called G, and G, and you see that G, they depend on where I am, X, and the past. So past events, so events that happen before my time T. So remember that here it means that it depends on X and T. So X, where I am in space. T is the temporal instant where I am right now. And we are saying that this rho is the product of another type of function that they come in 5 that depend on the past in space, past in time and in space. How they depend? Have a look at expression 5. This expression 5 has a kind of, let's say, decaying function with the spatial distance. You see it's 1, so it's like a constant 1 plus something. And this something has 2 parameters, theta and phi, right? And then we have an exponential of minus the distance in space. So clearly this is decaying. The larger the distance, the lower is the value of this expression, right? So the 2 parameters, parameter theta and phi, they have to be estimated. So this is a parametric function with 2 unknown parameters. And you see that theta provides the degree or the strength, if you want to call it like that, of spatial integration, right? In such a way that if theta is less than 0, then we have something like inhibition, which means 2 events, which means 2 people that are infected are kind of inhibiting each other, right? But we do not expect that, because in an infectious disease, if 2 people are, because of the contagious effect, we expect that 2 people that are close together, they have much more chance to get infected, right? So we expect that theta will be non-negative, but positive. But let's tell the data to give information about this theta. And then phi just provide information on how our function decays, because you see phi is in the denominator of the distance of the exponential. So it's kind of controlling a range of interaction. So strength of interaction on one side, theta, and range of interaction on the other. Range means, okay, that's fine. 2 people more than 2 meters, they will not be infected, or they have less chance to be infected, or more than 3 meters, or more than whatever number of meters. This is what is the range of interaction. Good. But yeah, so far, I mean, if we look at this, you could think of, oh, yeah, that's fine. This is a good approach, but there is no movement inside this expression. So what can we do with the movement? Fine, let's modify 5 to get into our modeling strategy, the human movement. And this is the expression you have here in this slide, in the middle of the slide. You see, so when we have 2 people that they are living in the same area, so this is why it's called here MA of xj equals MA of x. It means that if I have 2 persons living in the same area, that's fine. My g function will be just our f function. A function depending on the geographical distance. But if I have 2 persons living in different areas and they are moving from one area to the other, then I have to modify the f function. And the way we modify that is, you see this kind of, let's say, weighted sum. In fact, it's a convex sum, right? Where we have weights 1 minus the probability of movement times f plus the probability of movement times f. So this is the way we add into our modeling strategy the movement of people, right? And this is the kind of thing that we add into our modeling, because I mean this idea is something. I mean, if we just stay with 5, this is kind of something which is known in the literature, right? But let's say the good news here is that the movement data can be added into our modeling strategy, and then we can consider this expression here. Good. Well, this is just a graphical expression, but I'm just skipping it, of how to control this movement between different areas. Yeah, so now we go into now we have an expression for lambda, but of course there are parameters to be estimated, and we need some statistical inference to be done here. And this statistical inference is usually done through the log likelihood function. And you know that this log likelihood function is just the sum of the logarithm of the intensity minus the integral version in space and time of such intensity. But then we have a problem. How can we integrate in T and W, in space and time, our intensity? That's very complicated. So there is an option here. There is an alternative option here, which is what it's called the partial likelihood approach. So you see the difference between the first expression and the second. The second expression from a computational point of view, it's much simpler, much quicker to fit. Right? And this is called partial likelihood, which is fine. So basically the partial likelihood says that we just have to sum over all locations the log of a ratio, lambda divided by y integral. So you see that in the first expression we have double integral, in reality will be 3 because there are 2 for space and 1 for time. And now in expression 6 we only have 1 integral. So we've removed the integral over time. And this integral over W, which is a space, is just approximated by a sum, as can be seen in 7. So 7 is very simple to, let's say, to be given data, but to be optimized given data, right? And this is the thing we have to do to obtain information about theta and lambda. Fine. So just let's go quickly into the modeling results. This is the mu sub 0, so the temporal intensity function, the fitted temporal intensity function. You can see clearly the different waves we had there in Spain in 2020, starting, and then we have first wave, then everything increased, then we have something decreasing, and then we have a very strong third wave, something like that. So the temporal intensity is providing information on that. We also have information now on lambda, on the spatial intensity. That's perfect. We have information on how the number of cases are distributed in space in the region of interest. But we have something important here, which is, remember that the spatial intensity has one deterministic term, but also has some two non-deterministic, or let's call random effect terms, right? One is the spatial effect, and together with the relative risk. And here there are the maps corresponding to these things, to the spatial effect estimate, right? This has to do with U and V, if you remember in our term for the intensity, the stochastic term, the random terms, but also we can provide information on the probability of the relative risk. And this is very important for authorities. I mean, just for an authority to come to this kind of blue map, and you say, okay, this is the probability of relative risk. If it's, you say you can places where it's going close to 1, that's an important source of infection in your city. So this is very useful for taking decisions. So this is just an output of let's say the temporal intensity model. And finally, remember that the stochastic term in space and time is given by the two parameters theta and phi, and these are the expressions. Well, these are just numbers, and probably by looking at the numbers, you can say, okay, that's fine. I can see. Remember that theta is providing information on the strength, and phi is providing information on the range of the interaction. But if you look at numbers, sometimes numbers are boring, and it's much better if you look at this thing here. This thing here, what it provides is, you see there are two lines. One is a solid line. The other one is like the other type of line. And the solid line is providing information on this. You see that there is a decreasing behavior because of the exponential. And then you see, I don't know if you can see there on the screen, but this decreasing goes down to 10 are meters. And this is for us the range of interaction. So authorities, by looking at this, should say, no, less than 10 meters is raising the probability of infection. So people should be not only 2 or 3 meters, but just be on the safe side and be at least 10 meters apart, just to decrease the probability basically down to 0 to get infection. And this is given by our model, right? That's very, and then we have this theta 0.26, which is given information on the strength of our infectious contagious effect in our data. So yeah, so this is basically the output description of our mathematical model for Lambda. Good, and because time is running and I cannot go deeper into more details, but I really would like to go into the next section because it provides a different point of view, basically on the same problem. You see now that, again, we are in space and time, we are using point processes, but we are doing something different. For those working on neural networks, working on machine learning, you see the word neural kernels, and you will see what is neural kernel here. And we go into the non-stationary type of doing things. Well, again, we go back in this case to COVID data in terms of a point pattern in a city called Cali in Colombia. And this is the type of data we have for 3 different months, March, May, July, and August. You see a clear decreasing of number of cases in the space and time in this area. Now we are not using a mechanistic model, but we're using something which is called a Hawkes type point process. What is this? Well, this is just, well, this is important. I missed this one. There is one important thing here, which is, and we didn't consider that in my previous presentation in section 2, which is what we call landmarks. So there are particular places in the city that they provide a rise in the number of infections. For example, churches. People were still going into church for religious services at the beginning of pandemic when there was no quarantine. That was a place, a source for an increase of contagious. So churches on one side, schools, they were an important source of infections, right? Here we also consider the airport and some other places. All these places are called landmarks, and it is important for authorities to know which landmarks are raising our probability of being infected. And we add this information into our modeling strategy in this section 3. And that's very important, right? Good. Well, this is just some, let's say, descriptive plots. Let's go directly into what is important here. This, as you say, as I said before, we have a spatiotemporal point pattern. We have a history, which is the past history of our events. And then now, which is our modeling strategy. We go into something which is called Hawkes process, which is a type of self-exciting point process, right? And what is this? This is just something that provides information on lambda, on the intensity. And this intensity, you see it's given in expression 8 by 2 terms. One term is very simple. It's background intensity, something on the background, very easy to, let's say, to handle. But then the important term here is the second term. You see, the second term is given by the integral in space, the integral in time. Right? So this is the thing. So we have to model how the past triggers or affects future events. And the way we model this kappa function is basically essential. The best we can do there, the best model fitting and the best model strategy we can follow here, right? And this is our mission here, our aim here, to provide a very nice model for this triggering or kappa function. Good. So let's go into details. The usual thing of doing things, simple things, using a stationary kappa function. Stationary means that you can clearly identify in the top formula here a classical bivariate Gaussian density function. This is isotropic. This is a stationary. Everything here, but it's not COVID data. COVID data doesn't behave in a stationary way. So classical thing doesn't work. We have to go farther into details. let's go into non-stationary way of doing things. How we do this? We split this kappa function into two terms. One is a function that depends on time, this v function here, and we have another type of function that depends on s, which is space. So you see, kappa is divided into something depending on time, something depending on space. The expression depending on time is simple, and something we expect is again a decaying exponential function in time, which means what is happening today affects much more what will be happening tomorrow than what will be happening in 2 days' time, in 3 days' time, or in 10 days' time. Clearly, the effect of these dependency is decreasing in time. That's natural, and this is something that we know with this kind of infectious diseases. So the function depending on time is a simple function, but we want to go deeper into the spatial non-stationary part of the model. And we use an idea of Higdon in 1988. In 1988, he proposed an approximation to how to define a non-stationary Gaussian process. And what he did was something like, okay, that's fine. To approximate y, which is a general Gaussian process, I defined a number of nodes over my region. These are the UIs, right? I consider a kernel over the UIs. And finally, I consider the multiply of this kernel and just independent zero mean random variables. And then I sum up for all the nodes. With this simple expression, we end up with what is called y, which is a non-stationary Gaussian process. But this way of doing things in 1988 depended very much on the number of nodes. And it was a crude approximation depending on how many nodes. So what was the value of R, capital R, we use there. So what we use here is no, forget about nodes, and let's do a continuous thing over the whole region. So I fill my region by a continuous approximation, and I consider a non-stationary process. How to do that? Using what we call neural kernels. So this is our step forward from an approximation which is very discrete into a continuous approximation which is based on neural modeling. Fine. Well, I don't want to go deeper into the mathematical details because, again, time is running. But the general idea for this is the following. Our spatial function, and we are looking on the second row, v of s prime, is given by the inner product of what is called two feature mapping. And the inner product of these two functions is just the integral of the product of the function. This is classical thing, fine. But now, these feature functions, these phi s prime, are defined as a weighted sum of some kernel-induced feature functions, right? You see that phi s is given by the sum with r terms of some weights, w's, times kappa of s, which is a particular kernel. How many of them we have? R. So clearly our model depends on a hyperparameter, which is a capital R, that's fine. But the way we do this is very kind of, mathematically well defined, because you see on the very bottom of the slide, the way we define our let's say, spatial function v, which is given by the sum of the weights times the inner product of our kernel functions, right? So this is the way that we consider our non-stationary kernel, but we do even something more, which is the following. Again, our kernel functions could be Gaussian, that's fine, and Gaussian depends on a covariance matrix. This is something we know, right? And you know that the covariance matrix is if we use a Gaussian form, it's clearly isotropic. But based on a result which says that there is a one-to-one mapping between a bivariate normal distribution and its one standard deviation ellipse, we prefer to go into the ellipse framework. The reason is that COVID data doesn't behave like isotropic, like, kind of circle behavior. It moves around, or it spreads around more in the way of ellipse. So we change our sigma by the sigma you have in the bottom of the slide. Well, it could be a little bit more complicated from a mathematical point of view, but the only thing is that for ellipse, we need nodes. We need what we call focus, in fact, 2 focus points, and we need to define our axis, right? So this is what we do in this metric expression on sigma s at the bottom of the slide. But in any case, what we do is we consider ellipses rather than just circles. So we consider a non-isotropic version of a classical Gaussian distribution. Good. So, well, this is expression 11 is the way we model lambda to put into information 2 parts of the model. One part is our triggering function, as we just explained, and the second part here in this model is this gamma L G times G function is the way we put the landmarks information into our model. Remember, landmarks is particular places of interest in our city. Well, this is just a mathematical trick here. And let me just go into the details. So yeah, these are basically, but this is something very, very, very interesting. I don't know if you can see there on the whole screen, but the thing is that, yeah, that's fine. So what we have here is basically, you see, 3 representations of something that we can go into the authorities and tell them very particular details of how the spread of COVID is being produced in our city. You see there kind of red arrows. Some of them, they are sometimes they are going, let's say, from west to east. Some of them, they're going from south to north, southwest to so many different directions. So clearly they are identifying the main direction of the spread of COVID. And this is essentially important in our modeling task, because one thing is, yeah, we have a mathematical model for this, but another thing is how to explain this to authorities to take decisions. And the authorities, by looking at these graphs, they clearly can say something here. They can say, yeah, that's fine, in this part of the city, the spread is going from here to there. So let's take precautions here. Only in this other part, directions are very different. So we are able to model the main directions of the spread of COVID by using our approach. But not also that, but also we can see that depending on where we are in the city, the spread is clearly different. For example, on the left-hand side, we have the airport in the city. So in the airport, the intensity behaved in some very different way that, for example, in one district of the area, which is the second on the left, which is the number 15, they are called by numbers, or the third one is number 18, or finally number 1. So depending on where we are in the city, the intensity, which is the spatial spread of our COVID data, behaves very differently. So the message is, given a city, we cannot assume that the COVID behaves everywhere the same. It very much depends on where we are. And also, we can control the effects of these landmarks. Again, this is important. It's not the same being close to schools, close to hospitals, close to the airport, or close to very different places, because depending on how close we are, we will have a raise in the incidence of COVID. And this is what we call the effect of the landmarks. Yeah, and this is just finally the predicted conditional intensity. So our model, basically, we provide a model, we reinforce that our model fits well the data, and finally, we use the model for prediction into the future, which is also another important thing here, and why the statisticians are important for authorities, that we provide models for prediction into the future. Not only models that mimic reality, but also models that are able to see what will be happening in the future. Fine. And I don't know how many minutes I have left. Probably I'm... 10 minutes, that's perfect. That's perfect. So now let's go to the very final approach, which is section 4. As you see, the important word here is velocity. So every time we listened about the word velocity, velocity means space over time. So the motivation is, again, COVID data. So if we have COVID data and we know how the COVID data is being spread over a particular region, but if on top of that, we know how COVID spread is running, it means how much is running in terms of space over time, of temporal units, then we have some further information, because it's not the same that the spread is, it's kind of slow. Then there are some particular places where we identify that the spread is really high in terms of velocity, right? So again, we are motivated by that. So let's do something here. And we need something which is called velocity for a spatio-temporal point pattern. How can we approach this idea? Well, the idea we approached that was by using what is called spatial growth functions. So we have remove spatial, so we have growth functions. You know what is a growth function? So it's something giving information on the size, on the development of the size of a particular phenomenon. That's fine. But when we use the word spatial growth function, what we use is, okay, that's fine. We know how something is evolving in terms of size, but depending on the space, right? So our approach is given by this sort of formula you have in the middle of the slide, which says that our spatio-temporal intensity function, lambda, behaves as a particular stochastic partial differential equation. So now we enter in the world of, let's say, differential equations, but they are stochastic, they are partial differential equations, right? So, and this simple way of dealing this is like this. Differential of lambda is given by a particular R function. This R function will be our, let's say, growth process, our rate process of growth, right? Times lambda, differential of t. So this is our, let's say, our overall modeling strategy. But we have to put some restrictions here. Well, not that restrictions, but important points that this lambda has to satisfy. For example, if we need partial derivatives, we need lambda to be differentiable, right? So not all models of this form are useful for us. Only those models that provide a differentiable lambda, right? Because then we will be able to obtain partial derivative with respect to time, with respect to x, one of the directions, with respect to y, the other direction. Fine. Which type of models provide differential equations? Differentiability on our equations. So here you have just a list of 3 of them. And I mean, there are many, but I use these 3 because these are the 3 that we've been working with. So one is a classical linear, the linear ordinary differential equation, very simple expression, where you have this expression here. Differential of a general process x is given by R1 times x plus R2, differential of t, right? When this has a known solution, and the known solution you have it there on the first line, but we are interested in putting this into the framework of intensity of the lambda. So our linear ODE, the spatial analog formulation, will be this thing. Differential of lambda will be R, our rate process, times lambda, times gamma. And this is one possibility. It's called linear differential equation. But we have also the logistic version, or we have the Weibull version, right? I'm not going into the details of these 2, but again, we start from something which we know they are differential, and we put this into general framework, and then we consider the particular case of our lambda, which is our intensity, spatio-temporal intensity function, right? So in this context, just have a look at that. If you consider, and now I'm going directly into the third row of the slide. If you consider the partial derivative of lambda with respect to time, and you divide that by the partial derivative of lambda with respect to x direction, what you have is the partial of x divided of partial of t, which is a velocity at a particular location in direction x. Simple thing. Well, simple. I mean, the idea is simple in a sense, because we all know what is a velocity, right? But of course, we need then to develop this partial derivative, which will be a little bit more complicated. And in any case, based on expression 13 is very simple to understand. What it says is the probability that the number of points in a particular neighborhood, a small neighborhood, is 1. So the probability that I have only one event in a particular small neighborhood is given by lambda times the area of that neighborhood. The area is 2 epsilon times the area of S, right? But you see, lambda is playing a role there. There is an approximation of a probability of having one event in terms of our expression of lambda. And thanks to this expression 13, we can develop basically, which is our velocity. Why? Because now I'm going into 15. You see that what we have in the numerator, if you take the limit of the numerator, what we have is, I mean, we have lambda, just assume that we have a general function. In this case, is t plus incremental of t. So there is a change in t, s stays the same, divided over the increment of t. If we take the limit of this when increment of t goes to 0, this is what? This is a derivative, right? And the denominator is the same, but for space. Now t is fixed, and what we have is s plus h of u. So we have a space, a location in s, and then we have a u direction times a particular magnitude h. And again, the limit of this when h tends to 0, that's a partial derivative with respect to space. So the ratio of the two, we have a partial with respect to time derivative divided by something which is a directional derivative in direction u. And we are very close to the very final expression. Why? Because now, what is the denominator of this expression in 15? The denominator is this partial derivative, or let's call directional derivative in one particular direction u. You know that directional derivative is the product of u times the gradient. So direction u times the gradient of lambda. And the gradient, you know that it's a vector composed by the partial derivative with respect to one direction x and the partial derivative with respect to the other direction y. Right? So this ratio in 15 is providing all we need in terms of velocities. 3 minutes, perfect. So, and this is important. I'm very final comment in red in the slide is that because the directional derivative is in the denominator, right? We can evaluate the maximum or minimum velocity depending on particular direction. And in particular, you see in the bottom, what will be the maximum direction of change. This is called Umax. Umax, given by the gradient divided by the norm of the gradient, provides the maximum direction, the direction where I have the maximum change. So we have everything. We have directions where we provide maximum changes. We have velocities, so we have minimum or maximum velocities depending on that directions. Good. So yeah. So let me just now the only thing we need is to put some of these or the differential equations. Remember that I've named linear, I've named the Weibull, logistic expressions. There are many, but these three could be perfectly be used here. And here we have in number 16 the expression of the Weibull model. So we plug the expression of the Weibull model into our intensity framework, and we follow the whole theory starting from this 16. Well, there are things, but I'm not going into detail. Again, we use. I mean, some of you are let's say, are fond of Bayesian statistics. Here we use MCMC. just for the inferential framework in terms of estimation of our parameters, that's fine. I mean, it works perfectly fine. You could be using another type of inferential framework, but we decided to go into the patient. And because I'm going directly into the results, because I'm running out of time. So again, we go back to the Kali data. You know the Kali data because we've been using that in section 3. Again, we have a number of parameters in our model. So the parameters have to be estimated using, let's say, our Bayesian inference, MCMC. And the important thing is that as an output, we have as a one side effect, the estimated intensity function. In different temporal instance, we can say this is an estimation in, let's say, on April the 18th, estimation in June, estimation in August, in July, etc. So estimation of lambda in different temporal instance. This is the partial derivative with respect to time. So we can evaluate how much this lambda is evolving in time in terms of how quickly is the rate of change in time. Also, we can do the same thing with respect to direction X or to direction Y. And for me, the most important output is this one here. I think, I mean, it's kind of a small thing, but you can see arrows within the city. These arrows, they are indicating where the spread is providing the most rise. And you see, if you can just look at the data, the plots, you see that many of the arrows, they go in the direction of the hot spots. Sometimes the hot spot, which is these red things. So that's an indication of take care, because the spread is heading into this particular hot spot. So in 2 days' time, in 3 days' time, on the next week, you will have a very raised incidence in that particular location. So it's not only that it gives information on how the spread is being provided, but also it provides information on directions and where the spread is heading to. And that's the important thing here. For example, you can evaluate things like, okay, that's fine. I go to a particular area in my city. This is cell 911, whatever it is. And I see that the main direction there of the spread is in 294 degrees. And that's very useful information. Tell me where I am, and I can tell you where the spread is behaving and is heading to, which is the main direction there. So that is the thing. Good. So just to conclude, and just a few seconds, again, this was kind of motivation. I mean, I'm not pretending that everyone listening to the seminar has understood the whole thing, but the important thing is the general message that we have, in this case, COVID data in terms of a point part in space and time, that we need some kind of stochastic models and not deterministic models to provide models, mathematical and statistical models for our data. And point process theory can do this very easy, not easily, but can do this in a smooth way. There is something which is very important, which is real-time surveillance in space-time. When something is happening like COVID data, authorities, they have to take decisions day by day. And probably the decision that they are taking today is not valid for tomorrow, and tomorrow they have to change. The only way they can use useful information is by using our models that are being refeeded and rerun on a daily basis. And this is what we call real-time surveillance in space and time, right? Of course, there is a computational challenge in all these sort of things, especially because we have thousands and hundreds of thousands of data. Again, I mean, statistics comes together linked with computational challenge. So again, we cannot avoid all these computational challenges. And just a very final sentence saying that funny thing is that most of these models were used and are currently used in crime data analysis. And I have another seminar, but not for today, maybe just informal seminar, that I use some of these models, but for crime data. And this is funny. I mean, these models are abstract models and can be used for crime, can be used for COVID data, can be used for even for earthquakes. And this is the good thing with mathematics and statistics. Good. So thank you very much for your attention.
Thank you very much for Judge Mateo. Let's give the appreciation for Professor Judge Mateo. Okay, now I would like to open the discussion session. So we already have about 3 questions from the participants in Zoom. Okay, the first is from Titi Purwandari from Pajajaran University, also from Statistics Department. The question is, would you like to explain the validation of your models?
Yeah, that is a good question. Very well connected with the statistical practice, right? I mean, every time you provide a model, you have to validate the model. Well, the first thing is the way we validate is by using what we call prediction living out, live out prediction, which means we fit the model with part of the data, with only part of the data. So we live away from our model fitting real data, right? So we fit the model, and then we use the fitted model to predict into this part of the data that is being left out from the original data, right? So if our model is good enough, the prediction should be very close to the real data. So this is a usual way of doing things here.
Okay, thank you. For the second questions is from Fahmi from State Polytechnic of Lok Sumawe. Lok Sumawe is from the west part of Indonesia. So the question is how to ensure the given model is accurate. Is there any other comparison models, or is it possible to run this data in sample and out sample?
Again, this is a very good question. One of the slides I missed because I was running out. You can see here in this slide. Now this slide belongs to section 3. So we use this kind of non-stationary kernel, and you see up there it says in sample performance for 1 week ahead, right? So we evaluated our models in sample and out of sample. And this is important. I mean, in sample means that, of course, we have to, to fit a good model in sample, it has to recover what happened in reality. This is in sample performance, but also in terms of forecasting, we have to see that it's good for forecasting. So in every fitted model, we use both things, in sample performance together with out of sample performance. And this is the way we used, we use this here, but also we provided, I didn't show again the table, the previous table here. You see here, this again, I missed the table because I didn't want to explain the whole thing, but you see here that there are 3 quantities, 3 quantities here, MAE at 0.25, at 0.5, and at 0.75. And this is again a way to measure analytically in this case, the in-sample performance, right? So MAE, for those that are not familiar with this, is a kind of measuring the error in our prediction. So a difference could be a square difference or whatever, but the difference between prediction and reality. All right. So yeah, so that's also very important in terms of, let's say, quality of our fitted model.
Okay, thank you. I hope it answering the questions. For the last questions, also from Zoom, from Aswi Sukarna, Universitas Negeri Makassar, Makassar University in the east of Indonesia. The question is, in your temporal and spatial intensities model, how did you model the spatial term? Is there any reason for using Gaussian kernel function? And the last question is, what do you mean by stationary and non-stationary in the model?
Yeah, that's again, that's a good question again. So let me just go when we used these kernel functions. Yeah, so the idea of stationarity is very much connected with the idea of isotropy. Stationary means that the distribution in space, let's call about space, the distribution in space, if I shift all locations some particular distance, then that distribution stays the same. So it doesn't matter where the locations are. but just how they are connected between each other, right? This is the idea of stationarity, right? COVID data clearly is behaving non-stationary. This means that there are parts of the region where they are very close together, and because there is a clear dependence between them, and there are other parts where they are much farther apart. So the only way to control these changes of behavior is by using non-stationary models. But this is one thing in terms of, let's say, of shifting in a space. But the other thing is isotropy. The idea is that the interaction is not given by a clear isotropic model, which are the typical kind of circles in a space, but there are different ways of anisotropy that COVID, let's say, performs, right? And this is why we change from a classical Gaussian into ellipsoids or ellipses, using axes and using different focuses, just to control that the way of dependence in the spread is not isotropic in space. So the question is right when he says that we could be using other types of diffusion currents which could not be Gaussian. That's perfect. I mean, the idea is let's try to do the best thing and not complicate mathematics that much, right? So let's try to stick into Gaussian diffusion currents, but let's change what is necessary to fit our data. But clearly, the idea is open to any type of diffusion current, which could be not Gaussian. But in this case, being Gaussian, but just modifying from a classical sigma covariance matrix into, let's say, an ellipsoidal form, it works.
Thank you very much. I have also answering the question from the participant. Okay, I think that's all for the questions. And thank you very much again for Professor George. And I wish you a good health and good experience in Indonesia, because this is your first time coming to Indonesia. Very nice to meet you, Professor George Mateu. And let's give once again appreciation for Professor George Mateu. Please kindly receive our certificate virtually for the appreciation of attending this seminar as a keynote speaker. Oh, okay. I think we will give it. Okay. Okay, before we giving the appreciation to Professor George Mateu, I will give the time for Professor Hamzah Fansuri as a Dean of Faculty of Mathematics and Scientific Data to give a speech for the international seminar today.
Thank you. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning. It's almost noon here. Especially welcome to Professor George Mateu, from Spain. It's an honor for all of us here to get to come here to join our world-class professor program and also give the seminar today. And also I would like to also say thank you to all the speakers, and today will be also given by Dr. Igede Nyoman Mindrajaya. Is it correct? Yeah. And this today is starting from this morning, from 9 o'clock in the morning. Please accept my apology as well, because I came here late, about 30 minutes, and then just came just when you start or begin your presentation, Professor George. This world-class professor program is very good program, very excellent program for us to bring all the professor, very famous professor comes to Indonesia for and also to ITS. And this program is fully funded by our government. Yeah, and this program is also very competitive. We don't know how many applications were sent to the governments, but 82 applicants were called and also interviewed, and only 74 of them are funded. Yeah, and I'm, as the dean, very proud of it, because ITS received 3 grants, and 2 of them coming from our faculty of Science and Data Analytics. Yeah, thanks also to Dr. Ahmad Khairuddin, who is working very hard to prepare these ones, and also thanks to Professor George to put a lot of effort to come here to Indonesia. Welcome, Professor George, and welcome to Surabaya as well. In Surabaya is the weather is quite warm. Yeah, I think it's not very much difference as in Spain in couple months. Yeah, because in Spain it's still summer. Yeah, and it's also an honor for us to have you here, Professor George, and you have been given very interesting seminar today, the spatio-temporal points process model for the analysis of the infectious disease. Yeah, it's very interesting how we can predict the spreading of the like COVID-19 using the models that you develop, and that's the most interesting part is the last bit of your speech, that these models even can be used in other area like criminals and other things. So it's very interesting for me as well, although I didn't understand a lot about the science, the mathematics, and the statistics, but it gives me a good view of these applications. Yeah. As the Dean of Faculty of Science and Data Analytics, I also thanks to the Department of Statistics who arranged these seminars, and also to the Director of Global Engagements, yeah, where this morning Dr. Maria has given a speech, yeah, and also to all the organizers here. So I hope that with this program and Professor Matthew and also other speakers can have the following up programs, like probably join supervisor, join research, join publications, and if you also agree, I'm as the dean also invite you to become one of our what's called adjunct professor in ITS, and also to continue with our collaborations. Yeah, I hope Dr. Didin, I call him Dr. Didin, yeah, because if call Muhammad Khairuddin is Ahmad Khairuddin is too long, they call that just Dr. Didin. Yeah, I hope you can follow up these programs with other futuristic programs where we can do a lot of things together. We have things that may be useful to develop the science, also the model you have, also you do research together. We have also international program in statistics where students can also probably we can do exchange and something like this ones, do research together, and for this ITS also provides some funding, some grants for this kind of world-class professor. ITS also provides class professor like program. So it's similar to a WCP program, but this time is funded by ITS itself. Yeah. So that is my hopes for the future relation between us, between Dr. Didin with Professor George, and I hope so it will be further between ITS and also university. What again? Hame or Jama? Yeah, James. Yeah, James. Because yeah. I'm a bit confused how to spell Gemma, James or James. But I remember one of the MotoGP, MotoGP driver, he Jama Matia, yeah. The name is the writing is the same, Jama Matia. Yeah, it spells Jama. Yeah. Okay, I'm hoping that between ITS and Jama University, we can do further collaborations, and I'm as a dean will give all support that is needed to make it happen. That's all for me. Thank you very much, and also this token of appreciation for you, Professor George. Yeah. Certificates of giving this seminar.
Thank you very much.
Thank you.
Thank you.
Oh, yeah. No, wait.
Okay. Thank you for your words.
Okay, thank you very much for Professor Hamzah Fansuri as a Dean of Faculty of Science and Data Analytics for the remarks. And also thank you for Professor George Mateu for the good presentation and interesting discussion. For all the participants, we want to remind you that the link for the attendance would be shared by the committee through the Zoom or YouTube chat box during the seminar. So please wait if it has not posted yet. Now, we can continue to the next session. So the next session is the parallel session. The first is will be delivered by Dr. Igede Nyoman Mindrajaya from Department of Statistics, Faculty of Mathematics and Natural Sciences, Pajajaran University. He holds his bachelor's degree in statistics in 2003 from Pajajaran University. Then in 2009, he received his master's degree in statistics from Institut Pertanian Bogor. Then in 2022, he awarded a doctoral degree in special statistics from University of Groningen in the Netherlands. He has several excellent awards. In 2019, he was awarded to get the Taibot Prize of the Western Regional Science Association. And then in 2022, he had widely top downloaded article. Also in 2022, he got a cum laude distinction of his PhD thesis from University of Groningen. His index is 6, and if you want to know more about his research, you can check his ORCID page through the provided link. For today's seminar, his presentation would be about spatial temporal high resolution prediction and mapping, methodology and application to dengue disease. For Dr. Mindra, you can start the session, and we will have about 20 minutes for the presentation.
Thank you very much, Ms. Dwi. Let me share my screen first. Can you see my screen or my presentation?
Yes, we can see your screen.
Okay, very nice. Okay, thank you very much for the Dean for the Dr. Ahmad for inviting me to speak about my research topic, and thank you very much for the Prof. Matthew. It's very nice presentation, and honestly, I'm a little bit worried because a lot of my presentation part is have been presented by Professor Matthew. So I think it's quite easy for me to explain this part because have been explained clearly by Professor Matthew. Thank you so much for the nice presentation. Okay, let's we start with the topic or the title what in this presentation. I try to explain about the spatiotemporal high resolution prediction and mapping related to methodology and application to dengue disease in Indonesia. Okay, this paper already published in early this year. You can access the paper in the Springer, published in Journal of Geographical System. The detail about the derivative and also our code also can be found in that website. So today I'm not going to detail about the code or also the mathematical formulation, but try to explain the basic idea of this paper. Okay, dengue disease is maybe it's not very familiar in Europe country. Maybe Professor Matthew doesn't know about the dengue disease, but in our country, in Indonesia, it's beside of COVID-19. Dengue is a serious challenge health care worldwide, potentially leading to death, especially among the poor in low and middle income countries like Indonesia, Thailand, and even the developed country like Singapore. The dengue disease first time found in Surabaya in 1968, but until now, there is no effective vaccine, there is no medicine or specific medical treatment for dengue disease. So I think it's still a problem. It's still a problem for my country, especially in Indonesia or tropical and subtropical country. So what we have to do to minimize the worst effect, to minimize the consequence of the dengue disease, what we can do is try to develop control program, develop a prevention program to manage the transmission of the dengue disease. What we need to get information in fine spatiotemporal scale, so that in this paper we try to introduce how we can develop a model in a fine spatiotemporal scale to better manage and control the disease or dengue transmission. There is a complex thing today because COVID-19, maybe the attention of our government is quite little for dengue disease because all research focus on COVID-19. That's very bad things, I think. So there is maybe for the budget, for the prevention budget for the dengue disease is very low. So I think high resolution is one of the solution to cost effectiveness for the prevention of dengue disease. Okay, dengue disease typically involves spatiotemporal patterns. It's the same with COVID-19 also. The same with COVID-19 also. There is a spatial dependencies and there is also temporal dependencies. Yeah, and also high resolution spatiotemporal model and maps the distribution of relative risk, a basic element of early warning system, and at identifying where and when the outbreak will occur. So back to our previous, to manage and control the transmission of dengue disease, the best way we can do right now is try to find the spatiotemporal transmission at a high resolution or at a small area. But the problem in our country, as you mentioned before, as Prof. Matthew mentioned before, it's not easy to collect the data at the small region. For example, in Bandung, the data is reported in district area, but I think it's much better if we can estimate the relative risk at the village, for example, or kelurahan, for example, but there is no data in that space, that spatial scale. So how can we estimate the risk at the small area without the data at that area? That's become a challenge in this topic. Okay, if low resolution information is available, whereas high resolution cell level information is needed but lacking. That's, as I mentioned before, it's quite difficult to get the number of cases, number of information of the number of infected people in the small or small area, or for example in the village. So it's become complicated to get the good estimation, for the village, for example. Okay, area to cell disaggregation to join a cell estimation can be applied to obtain the missing information. So what we can do, we try to develop a model when we have the number of cases information at the district level. We try to use that information to estimate the risk at the small level, like a kelurahan or village. But we also need the information, for example, the covariate at the village level or the sub-district level. We call it in this paper is sub-district level. We have the information at district level for number of cases, and we need the other information, for example, the risk factor, like socio-demographic, like environmental information at the sub-district level, to try to get the estimation of the risk at district level and also at the sub-district level. That's the main idea, that's the motivation in this paper. Okay, this is a map of Bandung City. Yeah, Bandung City is divided, become 30 district and become into 161 sub-district. 161 sub-districts. So based on the information at the low resolution at district level, we try to get the risk estimate at the high resolution at the sub-district level. Okay, in this paper, we introduce the fusion or combine or joint area cell spatial temporal generalized geoadditive Gaussian field model. We abbreviation as FGGF model to generate high resolution at cell prediction based on observation at lower area resolution of the variable interest. Here, the variable interest is dengue incident and population at risk, and high resolution cell. We use the weather variables at the sub-district level, yeah, as the risk factor. Okay, Moraga et al. And Utasi have shown that the prediction performance of integrated area cell models can outperform models that use a single level data source. So I think using different scale of data is much better compared than if you only use the data at district level to estimate the data, the risk at the sub-district level without consider the risk factor at sub-district level. So we try to combine the data at district level and also the data at sub-district level to get more accurate estimate of the relative risk at district level and also sub-district level. Okay, the integrated area cell observation and combination of non-Gaussian data. We know that the number of cases is non-Gaussian, follows Poisson distribution, or Matthew mentioned before, it can be followed the negative binomial distribution. a nonlinear prediction and latent model component, in particular the spatial Gaussian field mixed estimation of FGGF models, prediction and mapping computationally complex and time-consuming. Yes, the last remark from the Professor Matthew mentioned a challenge of the computational process. Yes, we agree that when we try to divide the area become a small region, the computational cost is increased significantly. In this topic, we know as the big N problem. So when we use a small areas, we will have a problem of the computational computation. Okay. This issue can be handled by, however, don't worry, this issue can be handled by transforming a Gaussian field with a dense coefficient matrix to Gaussian Markov random field with a sparse precision matrix of the Mertens covariance. What is the problem when we use a dense covariant matrix? It's quite difficult to get the input of the matrix that we need to calculate the likelihood function, for example, and also for the estimation process. Okay, what our objective? The objective of this paper is to develop a high resolution prediction and mapping procedure for the spatiotemporal Poisson or negative binomial and applying a Gaussian area cell spatiotemporal generalized unit additive Gaussian Markov random field model, inference and prediction are handled in Bayesian frameworks. The approach will be subsequently be applied to dengue disease risk in Bandung City, Indonesia. Here we introduce two different distributions, first Poisson and second negative binomial. Why we need to introduce two distribution? That may be related to the question from the participant. How we can validate the model? We try to select the best distribution that fit for our data set. That's the one solution to get the good model for prediction and mapping the dengue disease in this paper. Okay, maybe here there's the simple illustration why this model, why is high resolution model is needed. For example, we have every district in Bandung City has a sub-district. For example, we call Lengkong. In Bandung, there is a district called Lengkong, has 6 district, sub-district. And every district has usually has one medical facility. Yeah, if a person infected by dengue disease, yeah, they usually come to the medical facility. Yeah, and the medical facility will report how many people infected to the health office. And usually they report only the district information of the suspect people, not all the information. Just okay, there is from the district Lengkong, there is 10 people positive by the dengue virus. They not list, for example, this sub-district A, sub-district B, sub-district C, but only report in global. So it's difficult to get the data at sub-district level. We only can access the data at district level. But for the cost effectiveness, we need the information at sub-district level, not at the district level. Because there is, as I mentioned before, the budget for controlling and prevention of dengue disease is quite low. Quite low. Nowadays, because the top COVID-19, there may be the budget getting low, and then compared to the previous years, because all the resources allocated to the COVID-19. So this is the big issue. So how can we get the accurate information at the sub-district level based the information that we can access at the district level? Okay, we have some literature that mention we can use the disaggregation regression model to estimate the risk at sub-district level based the information of the outcome number of cases at district level, and also the model will be validated and or fit by counting the information risk factor at sub-district level. So we have the information of number of cases at district level, and also we need the other information, for example, the risk factor at sub-district level. So we try to combine two different data from the two different scales at the district level and also at the sub-district level. Okay, as I mentioned before, if we only focus on the data at district level, maybe we have a misclassification issue because we will inform the estimate relatively will inform, okay, the district has high risk of dengue disease. But if we try to check more detail at sub-district level, maybe some district, sub-district will be categorized at no risk because there is no cases found there, all medium risk, maybe only one people infected in that sub-district, of very high risk because a lot of people at sub-district were infected. So maybe if we only focus on district level, there's a problem with the misclassification. Okay. What we can do to solve the problem? Yeah. As I mentioned before, we can combine the resource with what we have. We have the resource at sub-district level, for example, socio-demographic. We have the information about the environmental variable, for example. We can access the climate information for the resolution using downscaling model, for example. We can access the climate information from the World Climate Database with the resolution 5 kilometers, 0.5 kilometers. So we have some information at sub-district level, but we don't have the information of number of cases at sub-district level. We only have the information at district level. So we try to combine both of data and estimate the risk at the sub-district level and also at district level. So we will get two different estimation in sub-district level and also at district level. But yes, it could be not easy because there is a computational challenges, for example, big N problem, and also misalignment problem. What is misalignment problem? When we try to combine two different resource data at different level, that will misalignment occur that cause the bias estimate and also the increase of standard error of estimation. Okay, that's the problem that can be found if we try to combine or fusion the two different resources data. Okay, let's go to the basic model, the spatiotemporal generalized geodetic Gaussian field model, because we use a discrete data, so we use a generalized approach. Okay, consider we have a region A. This is we take for a simple illustration. We use regular data, but in the practical we use irregular lattice data. Here we just to make it simple. Okay, for example, we have a region A divided by 3 or NA different districts. Yes, and 2. We need to divide region A, using a grid for NP grid cell that we have done. We have the solution that we can do. We have region A, and we try to divide the region A become several grid cells that cover all of districts, and we using and we also can categorize which cell include district A, including district 2 and district NA. Yes, that we can that we have done to in developing this model. So we have the region, we divide the region becomes several grid cells. Okay, we have the region become several grid cells, and we will estimate the relative risk at based on the grid cell, and after that we apply block averaging to avoid the misalignments to get the estimation at the sub-district level and also at the district level. Okay, following the Moraga and also Jayan Palmer and also Utazi et al., we have two different level models. First, 3A. I'm sorry that the number in this question is follow the number equation in the paper, so maybe you can find number 3 and also next 6 the equation. So I keep the equation here, the number of equation here similar with the equation at the paper. You can access the paper because they're open access. So I don't want the reader confused with the presentation and the paper. So we keep the number of equation similar with the paper. Okay, we have the first equation at 3A. This is the equation for the district level. Okay, and the 3B, this is the equation for the sub-district level. Yeah. You can see for the covariate X-car, there's a bar notation. That means that we use the covariate is aggregated based on the sub-district level, and also P bar IT. It means that the component is also aggregated based on sub-district level. And we apply the spatial dependency omega I also to the sub-district level. So in this model, we have two different equations represent two different level of the data, district and sub-district level. And to avoid the misalignment problem, we will combine this both of this equation become a single equation, and then do the estimation of the parameter based on the single equation, not based on the both equation separately. Okay.
I'm sorry, Dr. Mindra, you have 5 minutes left for the presentation.
Okay, risk factor. I will include the risk factor. As I mentioned before, we use the covariate, the environmental variable of covariate to explain the effect of the covariate to the risk at the lower level and the higher level at district and sub-district level. We believe that the covariate is approximate, you mentioned before, is not stationary. So we allow the covariate effect is non-linear, and we apply the random walk process to allow the effect of the covariate non-linear to the risk factor. And also we introduce random effect components. As I mentioned approximately before, we use lyrics conditional autoregressive for spatial structure effect. And we might use Gaussian exchangeable prior for the unstructured spatial effect. For the temporal effect, we introduce the autoregressive prior. And for the interaction process, we select the best interaction component between space and time that mentioned that developed by Knoll in 2000. He introduced 4 different types of the interaction effect between space and time, type 1 and until type 4. Okay, we model the Gaussian field component, the last component, P bar, as I mentioned before, as autoregressive process. We believe that the process is constant over space but vary by time. This is the autoregressive model. Okay, we use a Bayesian inference here because we believe that if we use Markov chain Monte Carlo, maybe takes a lot of time to get the risk estimation. So here we use Laplace approximation. Maybe you all already know about the in-lab program that we can use to estimate the parameter based on the Bayesian as numerical base. We call it numerical Bayesian approach. We call in-lab. So it's inilah here to estimate our model parameters. Okay, as mentioned before, we try to combine to equation for the district level and equation at district level become a single equation. You can see in 13 equation here the equation based the combination between the equation at district level and the equation as and the sub district level. Here the detail you can find in our published paper. Okay, as I mentioned before, there is a common issue in if we try to combine two different resources data from the district level and the lower level at sub-district level. There's a misalignment issue. So based on Professor Crazy that mentioned in his publication, we can use block average procedure to stop the misalignment issue. We can see that the block average, this is the formulation to solve the misalignment issue in our models. So this is the joint posterior distribution. Okay, this is the Pusian area spatial temporal model. Yeah, I'm sorry I cannot explain in very detail here, but what we have done to combine and solve the dense covariant matrix. Yeah, we introduced the linear stochastic partial differential equation, and also Prof. Matthew mentioned before in his presentation. Yeah, we used this differential equation to solve the problem of the big N problem. Okay, for the regular lattice model, maybe it's not quite difficult to solve the PDA, but I think there's no space in regular lattice, but they present in irregular lattice. Census tract usually in regular lattice. So we adopt the fan in equation methods, yeah, to apply the SPDE for the irregular lattice models. Okay, this is then a small introduction of what is the linear stochastic different equation approach. This is the basic model in A1, and the PAM is the A2. We use this approximation, this method to stop the big N problem in our models. Okay, to estimate the equation in equation 13, we introduced two different metrics at once. Yeah, to estimate the risk at the district level, and also introduce the X2 to district level, X1 to sub-district level. So we have the final equation that we can estimate by means of R inla. Yeah, by means of R inla. This question 33. Yeah. Okay, this is the application for dengue disease in Bandung. We have, as I mentioned before, we have 30 districts and 151 sub-districts. This is the distribution, monthly distribution of the number of case dengue incident and also the standardized incident ratio. Okay, next we have the data. We extract the data from the WorldClimate database. We have precipitation, average temperature, solar radiation, and water vapor pressure for replace the humidity. Okay, this is the final model, and also if we use FAMS, we need to use triangulation. Yeah, we have to introduce the triangulation mass for Bandung City and the vertex edge with length 1 kilometer. Okay, this is the final estimation. Yeah, the spatial range, as Professor Matthew mentioned before, is related to the row at the previous presentation. The final spatial range around 14 kilometers because the high mobility in Bandung, so the dengue can be spread until 14 kilometers. And based on the covariate, we can see the water vapor has biggest effect to the dengue risk variation in the Bandung City. This is the fine tempering effect of the covariate, and we can see for the water vapor is constant over time, but the other covariate is varying over time. Okay, this is the spatiotemporal interaction for the area and also sub-district level. Okay, we have the posterior relative risk. Based on the model 33, we can get the posterior relative risk for the district level and also for the sub-district level. You can see this is for the Lancome. Yeah, not all region or sub-district in Lancome can be categorized as the high risk, for example, like this in mine. But if we use a district level, we may argue that or inform that all the district level at the sub-district level at the Lancome district so be categorized as the high risk area. But if we try to use the high resolution model, not all the district so be categorized as the high risk area. Okay, this is the accident probability. As Prof. Matthew mentioned, it is needed to categorize the probability greater or higher than 1, but here we use the threshold 1.25, not 1. Okay. Okay, this is the misclassification. There's a 15.6 misclassification if we use the district level data only, yeah, to try to estimate the sub district by the information only in district level. Okay, this is my summary and conclusion. Okay, effective and efficient control of variety of spatial problem, including Dengue disease, abatement require data at fine spatial temporal scale. However, data availability at the same, especially fine spatial scale, is quite rare. A major challenge in spatial science, including model infectious diseases such as dengue and COVID-19, is how to align database for different resolution consistently. In this study, we present the Gaussian area cell spatiotemporal generals geodetic Gaussian Markov random field model isolation. This problem, yes, we have present that we might solve the problem classification. Yeah, if we not use this model, for example, a high resolution model, maybe there is crucial issue of misclassification. Okay, I'm sorry, maybe I take time too long. This is the end of my presentation. Thank you so much.
Thank you very much, Dr. Mindra, for the presentation. We will have the discussion for your talk later after the last talk by Dr. Ahmad Khairuddin. Before we go to the next session, I want to inform you that if some participants miss some parts of the session, you can watch the replay of this international seminar series in our YouTube channel, Departemen Statistika ITS. Now, we can continue to the talk by Dr. Ahmad Khairuddin from Department of Statistics, Faculty of Science and Data Analytics, Institut Teknologi 10 November. I would like to read his profile. He holds his bachelor's degree in statistics in 2013 from Institut Teknologi 10 November. And in 2014, he received his master's degree in applied mathematics from Aix-Marseille University in France. Then in 2017, he awarded a doctoral degree in statistics from University of Grenoble-Alpes in France. And for the awards, in 2017, he received Mars Kusenbachse Prize. I hope I pronounce it correctly. And for the recent awards in 2022, he received Séjour Scientifique de haut niveau. I hope I also pronounce it correctly. And for the most recent awards, in 2022, in the same year, he is awarded a world-class professor program. His age index is 4, and if you want to know more about his research, you can check his Google sites through the provided link. For today's seminar, his presentation would be about log Gaussian Cox-Point process, a flexible model for earthquake modeling and poverty analysis. So for Dr. Khairuddin, you can start the presentation.
Okay, thank you, Bu Dwi, for the time. All right. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, almost to noon, everybody. So this is going to be the last talk for this seminar, and I'm really excited to talk about this. Of course, that actually I would also like to do some discussion with all of you here who come in the seminar. Actually, almost many part of my talk is already given in detail by Jorge. Actually, I talk, in Europe, we are not used to call like a doctor or professor or something like that, just call the name. And also given by Dr. Mindra. Before that, I would like to thank Dikti for the fund so that actually we can organize this seminar. And I would like also to thank the support from the ITS, especially Bu Maria, Professor Hamza, and Bu Kartika, and also Department of Statistics to support this seminar. And mostly I would like to thank, of course, all the speakers, Pak Mindra and also Jorge Matthew. We have been known each other for about 5 years now on 2017. And then we have many discussions, many collaboration. We have some works together. And then when I came back to Indonesia in 2019, and then pandemic just came, and then everything is changed, and then we just do online something, the one that I just showed you on the last picture. And I hope that this is not the, I mean, it could be the continuations of our collaborations. And of course, that if it is possible, I think that it would be also a good opportunity for us to extend the collaboration. For example, if some of the participants are probably interested to do PhD, either it is in ITS or in Spain, we can probably do some kind of joint supervisions about that and the other things that we can communicate later. So the talk that I'm going to talk today is based on these two Okay, so the talk that I'm going to talk today is based on these two work that I've been doing recently with my colleague, especially at the Department of Statistics and at Institute of Technology Polo November. So the first one was published last year in 2021 about modeling the earthquake occurrence by Cox processes. And then the second one is a going project in progress that now led by our colleague in the department, Pak Sutikno. This is about small area estimation, and we would like to link that with low-Gaussian Cox processes. Okay, so for the first motivations is on the earthquake, problem. So why we are interested in it, and actually when I came back to Indonesia, my first, thought that actually I would like to apply the model that I developed in Europe by doing a PhD and postdoc is that how I can do that on the earthquake data. Why? Because actually Indonesia is an earthquake prone area that if you can see actually on the picture that I have right here, that Indonesia is the meeting point of many, big plate, which is Eurasian plate, the Australian plate, and also Pacific plate. Of course, that if we count a Philippine Sea plate, it should be 4 plate. And not only just, of course, that Indonesia is the area that is very risk on the earthquake due to this geological area. But if we look at more closely on the specific part of Indonesia, the one that I have the box right there, which is called Sulawesi and Maluku, it is actually exactly the meeting point of that plate. So it means that this is very important to analysis because almost half of the earthquake happened or occurred in Indonesia, occurred in this area. So that's why the first part that I'm going to talk today is that the earthquake occurrence in the area of Sulawesi and Maluku. So the data that we have looks like this. Coordinates. So it's very related to one that Professor Matthew presented earlier. So the black dot that we have right here is the collections of the coordinates of earthquake. And then we would like to know how this earthquake are distributed. And then the next one is that we would like to relate this coordinate to the other, like say, geological variables. For example, the red line that I have here is the subduction zone. And then the blue line is the thrust. And the triangle, the red triangle here is the volcano. We're focusing here on the major earthquake, which means that the magnitude is greater or equal than 5 on the earthquake that occurred on Sulawesi and Maluku during 2009 and 2018. And then we would like to create a hazard map that involve stochasticity and then capture spatial trend and also aggregation. What does that mean about, for example, spatial trend? Spatial trend meaning that we would like to know how the earthquake occurrence distributed, whether it has a specific, say, tendency that actually the earthquake tend to happen in certain location more likely compared to the other location. In this case, it is probably quite clear that actually the coordinate occurred on the area of the north part of the Sulawesi and Maluku and also in the south part. So that we would like to know, is there any relation on that distribution on a certain, say, covariate or geological variables? And then the next one is about the aggregation. So for the aggregation, there are two, say, different terms. So the first one is that we would like to capture the seismicity due to the activity of the main shock and also the aftershock, because usually when you have a great earthquake and then near after, it tends to have another earthquake coming. And then the second one is the aggregation. That what we mean right here is that is there any random process that also affect the distributions of the earthquake occurrence, but we do not measure yet. For example, here is outside of these three geological variables. So to model that, we tried to use the Koch's model. So the Koch's model is that the double Poisson point process. Suppose that we have the non-negative random process capital lambda. If the condition of the capital lambda on X is a Poisson point process with intensity Koch's point processes, and also Koch's process. Okay, so to try like to model our data to this model. So what is the Newman-Scott-Cox processes? So probably I'm going a little bit slowly about this one. So is that so have generation main so and then after that, during the certain time, there is another earthquake that coming around the main shock. This is what we call an aftershock process. And then if we will do the union or the superposition of the of spring or the aftershock process, so that we can model this as a Newman-Scott-Cox processes. The flexibility of the Newman-Scott-Cox processes, or I just call that NSCP, is that the distributions of the spring around the main shock or distributions of the aftershock around the main shock can be determined using some probability density function. Like, for example, if it is uniform around the cycle, so that comes to the Martin-1 process. If it is a bivariate Gaussian, so it reduces to Thomas-1 processes. And the same if you consider Cauchy or variance gamma, so that becomes Cauchy and variance gamma point processes. So it means that we have some parameters to estimate that is due to this natural system or natural process. So the first one, number of because actually basically if we have data set, we don't know the number of the cluster or the number of the aftershock. And then the second one is dispersion parameter, which what we call omega, which is how the aftershock are distributed around the main shock. This is the first approach that I would like to fit on the earthquake data in Sulawesi and Maluku. Next is what I call Gaussian-Cox processes. So this model is also model for the aggregation, but with different types point of view. So the idea of Gaussian-Cox processes is that you have a random process. Here is actually capital lambda is the exponentials of Gaussian process with certain parameters, which is here is alpha and sigma square determining the covariance functions of the Gaussian processes. And then suppose that after you have your Gaussian process, and then we generate point pattern based or given or condition on this random process, so that meaning we have the Gaussian-Cox processes. So what is the idea under the applications of the Gaussian-Cox processes for the earthquake modeling? So because actually we have only 3 geological variables that are the subduction zones, thrust, and also the volcano, we believe that actually there are other covariates or other variables that also affect the distributions of the earthquake that we cannot take into account. So that's why that is represented by this random process. Good. So after doing some, of course, the estimation using some techniques that I don't want to go into very details, but of course that if you have any questions about that, I would be happy to answer about how to estimate the parameters. So the idea is basically we use the two-step estimation, which means that I would like to estimate the first order parameter related to the intensity function that is already detailed by Professor Matthew earlier. And then the second step is that I would like to estimate the parameters on the second order parameter that is I mentioned earlier here. For example, for the Gaussian-Cox processes, the second step would be estimating the alpha and sigma square. For the Newman-Scott-Cox processes, in the second step, we would like to estimate kappa and omega. All right, so the first step is to estimate the parameter related to the first order intensity parameter, and we call that spatial trend due to the geological variables, because I would like to know how the geological variables affect the distribution of the earthquake. Among 3 variables that we are considering in this study, which are subduction, volcano, and also thrust, we use the backward elimination to avoid the multicollinearity. And then we find that actually the base model is with these 2 variables, which are subduction and volcano. What can we remark from here? So the first one is that actually the sign of the estimate both are negative. That's the first point. What does that mean? So it means that actually if we have a location that is closer to either subduction or volcano, so that the risk of having earthquake occurrence would tend to be larger. Into more details, meaning that for the subductions, if I have a coordinate that is closer, so the unit experiment here is on 100 kilometer. So it means that if on the location that is closer to the subduction by 100 kilometers, so that the risk of having earthquake is increased by 1.4 or increasing by 43%. For the volcano, also increased by around 32% right here. So it means that if we compare, for example, between subduction and volcano, that subduction has a greater impact on the distributions of the earthquake that we have. If we go back a little bit on the distribution that we have right here, it probably a little bit makes sense, because actually here in the subduction zone is actually very close to the occurrence of the earthquake. So that could make sense that actually the subduction have a greater impact than the volcano. Okay, after analyzing the spatial trend of the distributions of the earthquake, and then the next one is estimating the second order parameter. So I denote that by C, where C contains kappa and omega for the Newman-Scott-Cox process, but it involves sigma square or alpha for the log Gaussian Cox processes. So we do for the second order parameter, we conduct using second order composite likelihood and also palm likelihood. All right, I'm not going into very details about how to estimate and also to interpret these parameters because of the time. The one that I would like to highlight right here is that I would like to compare all the models to find the most fit one by comparing the maximum likelihood that we have, meaning that I would like to find the greater maximum likelihood. So it means that it fit better than the other models. The second one is I use the AIC, meaning that I would like to capture, of course, that the how it fit the model, but also I would like to know regarding the complexity of the models, because in AIC we also consider the number of parameters included in the model. So for the second order composite likelihood, of course, that if we compare with Poisson, it is quite far away, meaning that Poisson, meaning that for independent cases, not suitable for the earthquake for very obvious reason. But for the clustered process, for the second order composite likelihood, they perform quite similarly. Of course, that actually here, probably if we can look a little bit closely, so Gaussian variance gamma a little bit outperform than Thomas and log Gaussian Cox processes. For the palm likelihood, the log Gaussian Cox process outperform a little bit than the other Cox models. And then for the validation, of course, and as a statistician, we always like to ask ourselves that actually either our models is good, and also it's also questioned by our participants earlier on the talk by Professor Matthew. So to validate our models, we can also use the envelope. Envelope in our case is K function. So the idea of envelope, if you are not very familiar with, is that actually looks like confidence interval. So the one that we would like to see here is that how our fitted model can relate to the real data. So basically the one on the solid line, the black solid line here is the real data, and then the red dot is actually the average of our estimate of the K function, and the gray area is the interval, meaning that we have the minimum and the maximum. So the idea is that we would like to have the gray area that is close to the solid line and also not too white. For example, if I look at the F here, which is the Thomas process using second order composite likelihood, of course, that it falls into the gray area, which is good, but the variance is quite high because the gray area is quite large. So among these 9 models, probably that we can see there are a couple of models that works quite well. For example, that we show you earlier using the cosivariance gamma, and of course also the Logos and Cox processes. For example, here in I is the Logos and Cox processes using palm likelihood, which is performed quite well. Okay, so the concluding remark for the first one is actually Cox process outperforms the Poisson point processes, and the Logos and Cox process shows flexibility to model earthquake occurrence. I'm just going for the second one, but probably a little bit quick for this one. So the motivation for this study is that actually it's already sampled some household in sub-district level. So in Indonesia, we call that a level kelurahan atau level desa, and then we call that a sub-district level. And then larger region, for example, if we have sub-district, or we say that village, or we say that desa kelurahan, and then we have also a district level, and we have a region level. So the idea is that we would like to know the per capita estimation on this one, because we did not do like survey for all the household in the entire like region, but we do only several households that is sampled using some technique, sample technique. The question is in which level it should be conducted, the estimation of the per capita, either used on the district level, on the average in it's right there, and we can also do in region level. However, actually, if we look at the locations of the household that is sampled, and I plot that, actually it is a point pattern. And then, but it is not the full point pattern, because actually it is not all the household that is in the area, but actually it is a sampled. So that's why I'm going to do thinned point process, that actually with some thinning probability, I would like to know first one is where I can find the sample of the household. And the second one, the most important one in this study is that I would like to know in the location that is not sampled, I would like to know what is the per capita or income of the household. And it's very interesting. Why? Because actually the first one that I can show you here, the topography, the north one is this. So I just rotate to have more visibility. Is with lower altitude and to have greater income rather than in the southern part, which is in a mountain which have rely on the agricultural sector. So we would like to know more about how does that give an impact on the income. So to do that, so we consider marked point pattern, this data. So we have like 5, meaning that it is on a scale of a million. So so it means that it is 5 million, it is 15 millions. And then we do mark log Gaussian Cox processes, considering thinning procedure to model the intensity, considering that actually the intensity is independent between the point process and also the mark, which is sometimes makes sense. That's also a thing that earlier on the talk by Professor Matthew also considering like some multiplicative part of the spatial temporal. Here in this case is mark and the point process. And then we would like to compare with the regional based modeling. So the result is like that. So we do 3 regional modeling. We call that direct estimation, which means that I would like just to estimate the area, which means here in the district, the average of the income by only averaging the one that we sample. And then the EBLAB and CBLAB is the small area estimation model that we would like to also model based on this district level. And then Mark, Logos, and Cox process, the one that we propose is that we would like to estimate the per capita into more details in the location or in the coordinate level. And it turns out that actually our model work well by the root mean square error that is almost 10 times greater than the CBLAB. Probably this could have visualization about the estimate of the per capita considering EBLAB, CBLAB, and Mark-Logos and Cox processes. One that I can show you or I can point out is that for the EBLAB tend to overestimate on the northern part because actually mostly it is a which great, and then but it underestimate the per capita on the lower part or the southern part of the Kendall area. For the CBLAB, it improves EBLAB by considering the topography, the spatial dependency due to the work that people done, right? They can be considered in the model, but again, that actually in one district, they assume that the average or assume that actually the per capita is the same, which doesn't take into account the variation within the district. And the good job of the process is that we can do that into more details, meaning that, for example, if you look at the southern part of the Logos and Cox process that we have right here, it varies it varies a little bit compared to the CBLAB, for example. So that's why it may perform better than the other models. Okay, so to close the session, I would like to give some possible extension that we can discuss or we can and I'm looking forward to the discussion. Thank you.
Thank you very much, Dr. Khairuddin, for the interesting presentation. Now, I would like to open the discussion session for the talk by Dr. Mindra and Dr. Khairuddin. So for all the participants, you are allowed to have any comments or remarks or questions, and you can either type in the Zoom or YouTube chat box, or you can give a raise hand to ask directly to the speakers. So we could start the discussion session now, and I would like to please you all to give any question, remarks, or the comments. There is one question for Dr. Mindra. The question is, how did you evaluate your model? Then did you use a sensitivity analysis in your models? And the last question is, what should we do if some of the model fit measures we use give different results? The question is from Aswi Sukarna from Universitas Nasional Malang, Universitas Negeri Malang.
Makassar.
Sorry, Makassar.
Yeah. Okay. Thank you very much for the very nice question, Ibu Asri. Long time no see. Okay. Yes. We have several procedure to get the best model from our data set. For example, in Bayesian approach, we can use probability integrated integral, for example, GPO, for example, and also compare the several model using deviant information criteria, also WIC, check the MPL and also R-square to check to define the best model for our data set. And for the sensitivity analysis, yes, we have done for sensitivity analysis. Yeah, we have tried several prior distribution for our random component. For example, gamma prior distribution, also half-Cauchy prior distribution, uniform prior distribution, and the last we check for penalized complexity for all the quite for the that used to estimate the is quite different. So we applied use different prior distribution and distinct research, we might use the model information criteria or model comparisons to find the best model for our data that we have done in our papers. Thank you.
Okay, thank you very much for the answer. I hope it answering the questions. And for, I have a question for Dr. Khairuddin. Because I'm not really deep into the special statistics, I want to ask, is the Gaussian-Cox point process considered the time effect in the model?
Okay, thank you, Bu Dwi. So basically, all right. Okay, so basically the one that I consider right here is that the specific case of low Gaussian-Cox processes. So it only considers the locations of the earthquake. So that's why we model with spatial low Gaussian-Cox processes. Of course, it is very possible to extend that on space-time, meaning that it names spatio-temporal low Gaussian-Cox processes. There are a lot of studies, there are a lot of works working on that particular model. That would be also important that we consider in the earthquake. The main problem or the main issue that why we do not do that yet is that the first we would like to know further about how it is distributed spatially. For example, the one that I showed earlier to you and the other participants is that, okay, I see that the earthquake tend to appear in the north part of Sulawesi and Maluku. So that's, I mean, the main aim first. And then the next one, probably it could be possible to extend that on whether there is time interaction between one earthquake to the other earthquake. One possible extension as well is that to consider like conditional intensity based model, like the one that presented by Professor Matthew, using like ETAs, using Hawke's point processes, that we consider the time effect on that as well. So meaning that we know by the history of the precedence of the earthquake, we probably can consider what is going to happen about the risk of having earthquake in the next time. I hope that.
Thank you very much. Actually, I'm asking that question because for the earthquake, usually it's not just appear in a particular area. Also, it has the time effect. Of example, in a year, it appear several times. Maybe a year can be 5 times or more than 5 times in a certain area. Okay, thank you for the answer from Dr. Due to the time, I think we can end the discussion session for Dr. Mindra and Dr. Khairuddin. So thank you for Dr. Mindra and Dr. Khairuddin for the good presentation and also for the interesting discussion. Let's give the appreciation for Dr. Mindra. Please kindly receive the certificate virtually as the appreciation of attending the seminar as one of the speaker in the parallel session.
Thank you. Thank you.
And also, please kindly receive for Dr. Khairuddin for the certificate virtually as the appreciation of attending this seminar as a speaker also. Thank you very much for the speakers.
Thank you.
In the Zoom and YouTube chat box. And for some of you that missed some parts of the sessions, you can also watch the replay of this international seminar series by going to our YouTube channel, Departemen Statistika ITS. And also, if you are interested in getting more information about recent news or announcement from Statistics Department, you can also jump into our website and follow our Instagram page in @its_statistics. Lastly, I would like to thank all the speakers, Professor George Matthew, Professor Hamzah Fansuri, Associate Professor Maria Anitiasari, Dr. Igede Nyoman Mindrajaya, Dr. Yudi Andriana, and Dr. Ahmad Khairuddin. Also, I would like to thank all the committees that has been supporting this event from the beginning until the end, and also all the lecturers and the participants who attend this event. Moreover, I also would like to apologize for any mistakes and troubles during the seminar. We wish to the development of statistics. Thank you very much. I will count down from 3 to 1. Okay, I will count from now. 3, 2, 1.
Thank you.
Thank you very much.